Hello. First, I want to thank Professor Hojo Lee for this opportunity to talk. And my topic is volume-constraint local energy minimizing sets in a Bohr. This is a preprint, and you can see the archive number here. And this is a joint work with my advisor, Professor Chao Xia. I will divide my talk into 4 parts. For the first part, I'm going to give a brief introduction and state our main results. Let's start from the free boundary hypersurface. We consider the volume constraint variation among C2 hypersurfaces. First, we consider set omega in the Euclidean space Rn, which is open, bounded, and with a C2 boundary partial omega. Say this is omega with a C2 boundary partial omega. Then we consider C2 hypersurface M in omega, such that the boundary of M lies in the boundary of omega. Say this is M, with its boundary lies in the boundary of partial omega of omega. Then omega is divided into 2 parts, and we denote one of the portions by E. Say this is E. This is M and this is E. Then we consider C2 diffeomorphism psi, which is said to be a volume constraint variation if psi 0 is the identity map, which maps M into M. And for a small time t, we have the image of E under psi t has the same volume with the original set E. So this is E, then psi te is this, which has the same volume with E. And moreover, we want that psi t maps the boundary of omega into the boundary of omega. So if this is psi te, we want psi t maps the boundary of omega into the boundary of omega. Then we denote the parameter of E in omega by Pe omega, and which is simply given by the surface area of M. So the surface area of this guy is defined to be the parameter of E in omega. And finally, a C2 hypersurface M is said to be a volume constraint parameter minimizer. Among C2 hypersurfaces in omega, if for any admissible variation psi, which is defined above, and for any small time t, we have the parameter of E in omega is always less than or equal to the parameter of psi te in omega. So this part has the surface area of this part is always less than or equal to the surface area of this part, which shows that M is a local parameter minimizing set. Then we have the following fact. Bistationary, or we can say that if M is a critical point of such functional, the parameter functional P psi te in omega, if M is the critical point, then we have the geometric information that M is a CMC hypersurface and intersects partial omega orthogonally. Say this is omega, and M is the critical point of this problem, then M must be looked like this. M intersects partial omega orthogonally and has a constant mean curvature in the interior. Precisely, if we denote nu M to be the outer unit normal of M, and nu gamma M to be the outer unit conormal of M along partial M, and x to be the initial velocity of the variation, and h to be the mean curvature of m here. Then, from the first variation formula, we have the first derivative of the surface area, and it's this guy. And from the divergence theorem, we have the first derivative of the volume, it's this guy. And since psi t is a admissible variation which preserves the volume, so we see that this guy must be 0. And since m is a critical point of such functional, we see that the surface area, the first derivative of the surface area must be 0. And from this two relation, we see that we can have the geometric information as above. And we will give a detailed proof in our main theorem, so we just skip the proof here. And since m is not only a critical point of the functional, but also a volume constraint parameter minimizer, we have the stability. And precisely, we have the second derivative of the area functional, or the parameter functional, must be bigger than or equal to 0. And by a special choice of the variation psi t, precisely, if we consider x, the initial velocity, to be f times nu m, where nu m is the outer unit normal, and f is any smooth function defined on the whole Euclidean space Rn, which satisfies that the integration of f over m vanishes. So we consider, for example, this is f times nu m. This looks like this, where the integration of f over m vanishes. Then we can see that under such variation, within a small time t, that psi t e has the same volume with e, which shows that x is an admissible variation. So we can use this variation to test the stability and to have the following formula, the following inequality, which we call the Pancreatic type inequality. And the reason we call it Pancreatic type inequality is because for this term, we can view it as the tangential divergence of f times the tangential gradient of f minus the norm square of the tangential gradient of f. And for this guy, if we use divergence theorem, and we will see that it is the same with this guy. So finally, we will have the L2 norm of the tangential gradient of f bounce the integration over m of f squared times the second fundamental forms norm squared plus the boundary term f squared times the second fundamental form of the boundary takes in nu m. So we see that the L2 norm of the gradient bounds the L2 norm of F, which is indeed a Poincare type inequality. And now we extend the above result to capillary hypersurfaces. For the capillary hypersurface, we consider instead of parameter functional, but the free energy functional. We denote the free energy functional by F beta E omega, where beta is a constant, which is bigger than -1 and less than 1, and is defined by the parameter of E in omega minus the parameter of E in the boundary of omega times beta. Say this is omega, and this is E, and this is M. Now, in addition, we consider this part. We call it B plus. Now we consider the surface area of this guy minus beta times the surface area of this guy. And for such functional, if it is a critical point, if M is a critical point of such functional, then we will see that M is a constant, M is of constant mean curvature and intersect partial omega with a constant contact angle theta, which looks like this is theta. This is M. And if for a special choice that beta is 0, then by this relation that cosine theta equals to minus beta, we see that theta must be half of pi. So which reduced to the case that M intersect partial omega orthogonally, which means that M is a free boundary hypersurface. And moreover, since M is a free energy minimizing set, we have the stability. Also, with a special choice of the initial velocity, we can test the stability to have a Poincare type inequality. So in a word, for free boundary hypersurface and capillary hypersurface, first we consider if M is a critical point of such functional, then M has some geometric information which shows that M must be CMC and intersect partial omega with a constant contact angle. And from the stability, we can derive a Poincare type inequality. For these two results, they are well known in the last century, and we see that they come from the critical point of functional. And if you have some knowledge about geometric information, you will see that sets of finite parameter are natural geometric objects for when considering calculus of variation. So it is a natural question to ask if we can extend such results to sets of finite parameter from hypersurfaces to sets of finite parameter. These are smooth and these are not. And the answer is yes. First, let's briefly introduce the definition of set of finite parameter. We consider the most simple case, the set of finite parameter in the Euclidean space Rn. For a set E in Rn, for example, this is E. It is said to be a set of finite parameter if the indicator function of E is a BV function. And for the definition of a BV function, it is like the total variation is finite, and the total variation is given by the following definition. We take the superman of such integration, where X is taken to be any C1 vector field with a compact support and with its norm less than or equal to 1. This gives the definition of the total variation. And if this guy is finite, then chi E is a BV function, and E is a set of finite parameters. And this is a nature definition because if we consider now E to be to have its boundary C1, then we can use divergence theorem here to see that this guy is integration over partial E of X times the outer unit normal of E. And with the choice that X taken to be exactly nu E, then we can attain the superman, and this is this guy, and which is indeed the surface area of the boundary of E. So this is a nature definition. And a simple proposition is that if we consider C2 diffeomorphism for xi t, then if E is a set of finite parameter, then the image of E under xi t is also a set of finite parameter. Now we can state the main results. This was first derived by Stenberg and Tampron in 1998. They consider a boundary, a domain omega in the Euclidean space with its boundary C2 alpha, and in this domain, they consider a set of finite parameter E. Say this is E. This is E. Then, if E is stable for the volume constraint parameter list area problem, or we can say that E is a volume constraint parameter minimizer locally, and with that M denotes the set of the closure of partial E in omega, the closure of this guy, so the boundary part involved. And assume that M is C2 in omega, the closure of omega of a singular set, singular M, with a low Hausdorff dimension. For example, this singularity has low Hausdorff dimension, which is less than n-3. And we denote the regular part of M to be M minus the singular part. So we show this guy. Then the results are, first, since M is a critical point of such functional, so we have the similar result as before, that the regular part of M inside omega has a constant mean curvature. And near the boundary, we have M intersect with omega orthogonally. And moreover, from the stability, we have such Pancreatic type inequality. which satisfies for any smooth function with its integration over M vanishes. And now we consider that omega is taken to be a Euclidean Bohr, which is a special case. There are a few results about this. In 1997, Rose and Sohm proved that totally geodesic bores and spherical caps are capillary stable. And in 2019, Wang and Xia proved the inverse. They proved that any stable immersed CMC hypersurface with a capillary boundary in the Euclidean Bohr is either a totally geodesic Bohr or a spherical cap, which shows that for Euclidean space, for Euclidean Bohr as the ambient space, then the stabilizer, the stable CMC hypersurface must be like it's either a totally geodesic Bohr or a spherical cap. These results are for hypersurface, but if we consider Sternberg and Champrun's results, they consider the set of finite parameter, which is not smooth in general, and combine this result with Wang and Xia's approach. With some modifications, we can see that such M must be totally geodesic or spherical caps. And above are our motivations. It is a natural question to ask if we can generalize this result to a capillary case, for a set of finite parameter. So now we have to consider the parameter functional instead of the free energy functional. And we also wonder if a stable capillary set of finite parameter in a Euclidean space has some rigidity as before. Since Sternberg and Champrun's results only prove that the stable free boundary hypersurface has some rigidity. Yeah, and here are our main results. We proved that if E is a set of finite parameter and stable for the free energy functional with a low Hausdorff dimension of the singular part, then similarly we have the geometric information that the regular part of M inside omega must be CMC, and the regular part of M must be intercepting the boundary of omega with a constant contact angle theta, where cosine theta is minus beta. And moreover, from the stability, we have the following Pancreatic type inequality. And that's for a general omega with a C2 boundary. And in particular, if omega is taken to be a Euclidean Bohr, we have some rigidity results. Now, if E is in the Euclidean Bohr, is capillary stable set of finite parameter with a low host of dimension of the singular part. Then we have the rigidity that M is either a totally geodesic wall or a spherical cap. And this result proved the regularity by the stability. And that's my first part.